Every bridge you've ever driven across, every skyscraper piercing the skyline, every tunnel, dam, highway, and airport runway, they all share one hidden enemy: concrete cracks. For nearly 2 centuries, engineers accepted this as an unavoidable law of physics, so they came up with a workaround. They buried steel bars inside the concrete before it hardens. Concrete handles the compression, steel handles the tension. Together, they created reinforced concrete, the backbone of nearly every major structure built since. It was a brilliant fix, for a while, because steel, it turns out, comes with its own expiration date. Steel rusts, and when steel rusts inside concrete, it doesn't just weaken quietly, it expands. Rust takes up more space than raw steel, and as it swells, it pushes outward, cracking the concrete from the inside. Water gets in, salt gets in, especially near coastlines or roads treated with de-icing chemicals in winter. The cracking accelerates, the corrosion accelerates, and eventually the entire structure begins to fail from within. This isn't a rare problem. It's happening right now, underneath your feet, in almost every major city on Earth. Governments spend hundreds of billions of dollars every single year repairing corroded, cracking concrete infrastructure. Bridges get shut down for inspections. Highways get patched over and over again. Parking garages, some barely a few decades old, get condemned. In the United States alone, tens of thousands of bridges are officially classified as structurally deficient. It's one of the most expensive, most invisible problems in the entire built world. For 150 years, nobody solved the root issue. They just kept managing the decay. Then came a different idea. Not stronger concrete, bendable concrete. Researchers first developed the science behind this decades ago, but it was engineers and material scientists in China who took the concept and pushed it into real-world large-scale use, refining it, mass-producing it, and deploying it in actual infrastructure projects. The material became known as high-ductility concrete, or HDC. Here's the twist. HDC contains almost no traditional steel reinforcement at all. Instead, engineers mix in something almost absurdly simple: tiny synthetic fibers, thinner than a human hair, made from a plastic called polyvinyl alcohol, or PVA. These fibers are scattered evenly throughout the concrete mixture, like microscopic threads woven into fabric. And that's when something strange starts to happen. Ordinary concrete, when it fails, forms one large crack. That single crack keeps widening under stress until the material eventually breaks apart completely. It's a single point of failure, like a plate shattering. High-ductility concrete fails differently. When it's placed under stress, it doesn't form one big crack. It forms thousands of hairline micro-cracks spread out across the surface, each one no wider than a human hair. Instead of concentrating all the stress into a single weak point, the material spreads that stress across an enormous network of tiny cracks. Imagine bending a sheet of paper versus bending a sheet made of thousands of tiny accordion folds. The folded sheet can flex and absorb the motion. The flat sheet just tears. That's essentially what's happening inside HDC. The fibers grip the cracks as they form, preventing them from opening wide or spreading uncontrollably. The result is a material that can bend, stretch, and even take repeated impacts without snapping. Some versions have demonstrated the ability to deform far beyond what ordinary concrete can handle before failing, all while remaining structurally intact. So why does this actually matter beyond the lab? Because a material like this could quietly transform how we build everything. Bridges that resist earthquakes better because the structure can flex instead of shattering. buildings that develop far fewer catastrophic cracks over their lifetime, roads and repair patches that last years longer because there's little to no steel inside to rust in the first place, lower long-term maintenance costs because fewer cracks mean less water infiltration, less corrosion, and fewer emergency repairs. In regions prone to earthquakes, this matters enormously. In regions with harsh winters and heavy road salting, this matters enormously. In aging cities with crumbling infrastructure, this matters enormously. But before you assume steel-reinforced concrete is headed for extinction, it's worth being honest about the limitations. High-ductility concrete is still significantly more expensive to produce than ordinary concrete. The specialized PVA fibers aren't cheap, and large-scale manufacturing infrastructure for this material is still developing. Building codes, which tend to move at a glacial pace, haven't fully caught up to this technology in most countries. Contractors are naturally cautious about adopting new materials for critical structures, and for good reason. A mistake in infrastructure isn't like a mistake in software. It can't simply be patched later. So don't expect every future bridge to be built entirely out of this material anytime soon. In practice, HDC is being tested and applied in targeted uses: bridge deck overlays, repair patches, retrofits on structures at risk from earthquakes, and other specific applications where its unique properties offer the most value. That's usually how transformative materials enter the world, not with a sudden industry-wide replacement, but through a slow accumulation of trust, one project at a time. And that's really the bigger story here. This was never just about inventing a slightly tougher version of concrete. It's about rethinking one of the oldest assumptions in construction, that cracking is simply the price we pay for building big things. Material science rarely makes headlines. It doesn't come with dramatic unveilings or flashy product launches. It shows up quietly, one bridge deck, one repair project, one retrofit at a time. And slowly, without most people ever noticing, it reshapes the cities we live in. Concrete has been part of human civilization for over 2,000 years. We assumed we understood its limits. So if one of the oldest building materials on Earth can still be fundamentally reinvented, what other technologies have we wrongly assumed had already reached their limits?